Hello everybody, I'm Oliver. I have made a image visualizer in Max MSP, so let's take a look into what we are handling. Now it looks like there's a lot going on. It's actually pretty simple. This is just a proof of concept. This does not fully execute the goal that I set out for. The original goal that I had set out with is that this will perfectly recreate an image in the frequency spectrum. I found some C documentation online that will give you a perfect recreation. This is a little bit more difficult than that, and in fact did not work properly. Or it works, but it doesn't fully do the goal that I wanted it to. So let's go from left to right here. What we're looking at over here, the noise generation is just for texture. It's not important to any sort of calculation that happens. It's just going to the summation to the output. So we start here at the, this is the FFT. This is the entire process for running an FFT on a signal. It takes in a signal and it will output a list of values that you can then turn into a matrix. So you can see here from the JIT.matrix analysis is what is outputting. And this is just a basic configuration for what we're handling. And the in1 feed is just so that we can change the window size. So we're feeding it a window size of 2048. That's just what I settled on for this. You can kind of go with whatever. It is not super specific. This will then go into a dimension map, which inverts it. So right now it takes the list of values and then flips it upside down just to make sure that things at the bottom actually wind up at the bottom and things at the top actually wind up at the top. Otherwise, when it renders the FFT, the lowest frequencies will be at the top and vice versa at the bottom. Then we do a convolution here, and the whole goal of this convolution is this is what generates the FPS on the spectrum. This is what gives the illusion of moving across the screen. As we all know, when you run a live spectrogram, you'll see as you have time versus frequency, and then amplitude is the color. And so this is what helps it move through time. So you keep on pushing it over to the side and to the side because we're turning the matrix back into an image and then rendering out the image. So we then send the image over to this 3D generator, which we will cover at the end. This block up here at the top is just for covering the real world, the world rendering, which is where we create our objects. So this is the image extractor. This is actually very simple. It is not complex. There's just a lot of wires going everywhere. So the first thing you do is you use the import movie button to give it a file. You can give it a video file or an image. This only works with images. I have no idea what would happen if I threw a movie into this. And I used Minecraft skin textures as my test images. They turn out to be a great resource for this. They are low resolution, which means rapidly cycling through, and they have lots of colors usually, and it's pretty easy to download a lot of them and just run different tests. So what we're doing is we're turning the image into a matrix. This is essentially saying, every pixel has a coordinate, and then it has a certain alpha, red, green, and blue value. So this is actually a matrix of matrices. It is four layers, the alpha, red, green, and blue. So the first thing we need to do is unpack the image matrix into 4 separate matrices to make sure we can get each of the data individually. Then we will unpack the value of the brightness of the color at the given cell, which is our coordinates, using this configuration here. And the reason this is unpacked with 5 zeros is because the output from this is x coordinate, y coordinate, and then it says cell, x coordinate, y coordinate, value in text, and then it gives you the actual numerical value. So you want to take the 5th value out of that list that it's being output and use that as our information. This block here now is just the counter. This is basically using a for loop that runs, we're using the given dimensions of the image that you feed the program. So the reason that we subtract 1 off of the image is because the indices go from 0 to 63 rather than 1 to 64, so we need to account for that. And then these TBIs are basically just so that when you update the information coming into it, it sends out a bang. And you need to send out a bang to operands to make sure that they actually execute and then spit out their own value. So this is just a counter, and then we log the X and Y coordinate of where we are presently. When the Y counter, which is on the vertical axis, hits its maximum value, so all the way at the bottom, it sends a bang to the X counter, which then moves us over to the next vertical column so that we can render through the next chunk of the image. Oh my gosh, I'm already at almost 6 minutes. All right, we're going to do this quickly. This over here is just some division work to make sure that the image rendering knows how many steps we're going through the frequency domain. This runs from 2,000 up to 16,000 hertz, just to give it a little bit of a buffer. It's supposed to give it a buffer on either end. So this is just doing all the math to figure out, okay, how many steps are there, which is just the vertical aspect ratio, and then how many hertz are we stepping by on every step. We then feed all of this information into these ZL groups. The way that these work is that you give it a size, and then you start feeding information, and it will log each new bit of information into a slot. Once it hits the maximum amount of slots, it combines them all into a list, which is a type of variable in Max, and sends that list out to wherever it's going. So this will store the 64 brightness values in the column, and this will store the 64 frequencies that it needs to render out. If you send both of these to an MC, so we send this to an MC.sig, which converts a number into a signal, and we are making 64 channels, all so that we can do simultaneous rendering of all the rows at once. We then also feed the 64 frequencies into an MC cycle, which is basically just a cycle object of arbitrary size based off of what you feed it. We then combine those in a multi-channel multiplication signal with 64 channels, so that will amplify each of the frequencies by its corresponding brightness value from the matrix. So if we're looking at, index 1, which would be 2,000 hertz, we'll get the initial value from the matrix here, feed it into this one, into here, and then we feed 2,000 into here, and then we multiply them out. And then we mix everything down from all 64 channels into one single channel, and then we output that to the EasyDAC. Once we're there, we can actually start running this now. Let's see. So you can see here, this is the FFT. This is the live noise, and there we go. Now it's starting to read out some pixels. This is very loud in my headphones, and I do hope that Professor Lee had the volume turned down in there. This here is just a visualizer. This is what the actual spectrum looks like, and obviously this does not look like the image at all, and that is one of the big problems. What we're looking at right now is just information from the red channel of the image. So this is just the red values at apparently only 2 or 3 frequencies here, and so this is an issue where the tick speed is not fast enough in Max. So I'm actually going to get rid of that, and I'm going to pull up the cool little side project that I did for this. So this is a 3D space that has a 3D view of the signal visualization, so you can kind of see where some of the tones are. This will just cycle around and slowly start to erase things as it writes over it. But I think it's very cool. I had a lot of fun working on this. It was very difficult. There's not a lot of documentation for these applications of JIT and ZL and MC objects. But that is the project. Spectrars is still a work in progress. And my hope is eventually to get it so that I can print out images in color by overlaying all 3 frequency outputs. So thank you very much. I hope you enjoyed it, and I would take questions, but I am in my room and I am not there. So have a good one.